Welcome to the graveyard shift. So that's the title of my talk. Can you hear me at the back if I wander around? You still? Yeah? Okay, great. So a little bit about, you don't need to know too much about me. I've been around, I know a thing or two. My main, my preference, my main hobby is to be fiddling around in C and C++ code, hunting for difficult to find bugs. I do a bit of training, facilitating education, and I'm an occasional speaker. I don't have any 3-letter acronyms or 4-letter acronyms or Twitter handles to my name, and I'm okay with that. So, what is Grok? Why this talk? And this is just my definition. You know, as a developer, I came across Grok the problem because you really needed to grok the code to figure out what was going on and hunt bugs, fix the code. And I find that this kind of applies to security engineering as well. And I guess what the other side to this is you really need to understand the problem before you can start to fix things. And that's kind of important because I know Abate is an ethical hacking course, and you're going to find lots of security defects. You're going to write reports, and you're going to have this little thing at the bottom that says mitigation. And the tendency is to sort of brush over that. It's like do input validation, do BLAST, something very high level. And the client's probably going to come back to you and say, can you help me with this? Can you be a bit more specific? And it's at that point that you are going to need to understand a little bit more about the problem. So even though you've, a lot of you doing ethical hacking course, you will at some point need to be helping clients actually fix things. And so you will become a little bit more involved in what I would call solution engineering. That's the other aspect. You're not going to get away from it. And so I want to take you through a little journey down memory lane through some examples where this kind of stuff has gone wrong or backfired or something else has gone wrong. And just to sort of create a bit of awareness of how important this is. It's not just about the testing. You can't test security in. You have to build security in. And so this part of security is just as important as the hacking. So the motivation for this talk started with something very modest, a very sort of modest problem that I came across at work. And it was, how do I validate an XML document using a document type definition? The reason this is important is, input validation is the first line of defense. You get some untrusted attacker data, you perform input validation, that's the first thing you need to do. So it's the first line of defense. And imagine, I have two injection points. I think imagine we have 2 injection points in this document. So an attacker can inject in the red username, and also, by virtue of the injection, they can inject a role element into the document. This is like the example motivating why we need input validation. And then, of course, they can, inject the email at the bottom as well. And so, as a developer, as an application writer, you want to validate this document. Like it's got this role element that shouldn't be there. So I want to perform some input validation. So this is how you do it in Java. You transform the document to include a DTD. That's the code there with the important stuff highlighted. And then you load the transformed document with validation turned on. Simple. But. What if the document already contains a DTD? Then I'm vulnerable to all types of DTD entity attacks. For example, the document may contain a external entity that's referenced in the XML document that picks up the contents of a file or makes me vulnerable to a server-side request forgery somehow. So this is a problem. This is my Kung Fu 2 Panda moment, where Poe says, how does Kung Fu stop something that stops Kung Fu? The act of validating this document, performing input validation, makes me vulnerable to DTD injection. But at the same time, I need to validate the document because that's my first line of defense. So in the same way, how does input validation stop something that stops input validation? And so I had to think about the problem. I went to the Java docs, tried to understand the behavior. That didn't really help me. And eventually came up with a solution that is really, really non-intuitive. What you do is you first have to transform the document into another document that contains a DTD. It might still be the malicious DTD. And then what you need to do is create a validating document builder with a whole lot of stuff turned off, a special entity resolver to replace the built-in document type definition with your own. And then you have a validated document. And the lesson for me was that I had not thought through the problem space properly. I just said, do input validation. Just apply the DTD, go away, don't come back till you've done this. And so I realized that the solution space and problem space wasn't actually as simple as I thought it was. So I'm going to take you down sort of some more well-known things where something similar to this has happened. The first is XSS protection. So a cross-site scripting attack, we all know what that is. It's an injection attack that bypasses the browser's same origin policy, right? So here's a cross-site scripting. You have a vulnerable parameter that gets echoed back in the document. So on the left-hand side, I have name equals Super Mario, and that gets reflected back into the document. And this is an XSS because if I provide some HTML, I can get the familiar script alert. So here we have an XSS. And what XSS protection did is it looked at the URL in a GET request or the request parameters in the body of a POST request, and it held on to those, and it waited and waited, and then it got back the response, and then it compared the request to what was in the DOM. And if it saw something that looked like it had been reflected back into the DOM when the page actually loaded, then it did one of a number of things. It may have removed, it could report, or it could block the page loading, or it could simply filter out the offending script. So that's how it worked, but it's one of those things that has good ideas, but doesn't work the same way in practice. Firstly, you can imagine that you're making this request, you're holding on to the request parameters, and if you have a large document, you have to really scan through the entire document to figure out, is the pattern in the request in the loaded document. So there were some performance issues. But there were sort of more serious issues. For example, you could actually use XSS protection to remove important security code. So in this example, we have what looks like a cross-site scripting attack in the yellow, which is script call framebuster. Presumably, the script is to call frame busting code, so it's not loaded. It's not loaded in iframe. But the XSS auditor, the engine behind XSS protection, is going to strip this out. So in this case, it'll actually remove important security code. So if you do a bit of reading on this, this eventually started being deprecated by the browsers. They said, we can't support this anymore. There were actually loads of other issues. There was actually what's called cross-site leakage. So there were various other types of attacks. And there were ways to bypass it, all sorts of ways to bypass it. I mean, you could effectively, what the engine was doing was guessing what the security policy of the server would be. I mean, if you can imagine, if you had single quote S, single quote C, single quote R, single quote I, script, and that came back as script, the XSS auditor has to make a decision, well, is that a reflected XSS or not? Did the server application deliberately strip out those single quotes? What am I supposed to do here? So it has to guess, really, what the intention of the application is. And this is the policy in the browser, and has to guess for every single website. So there's a big debate going on, and actually the browsers already pulled it, but this was a bit of debate that was going on in the OWASP cheat sheet, and eventually they pulled it. But I submit that if we look at the anatomy of an XSS attack, reflected attack, the attacker gets tricks the user into visiting a site reflects it back, it's loaded in the page, script gets loaded. Here's the issue. The issue is in the server. The issue is at those 2 points: 1, not performing input validation, and 2, not performing output encoding. The issue is not here in the browser. And so I'm going to sprinkle little fortune cookies around this talk. You can take them with a pinch of salt, but they've got a grain of truth in them. This one I'm calling improper choice of protection domain, which is basically a fancy way of saying they considered the problem in the wrong place. It's a server vulnerability. They try to fix it with all sorts of clever stuff, and there was clever stuff in the client. So the next story is about certificate pinning. And this one's quite interesting because there was a lot of hysteria around certificate pinning, especially in mobile apps. And so I Googled certificate pinning, and this is one of the first hits I got. It says, why is HTTPS alone not good enough to protect our apps from the bad guys? And then it goes on to say, it's because any man in the middle can come between our app and our server and manipulate data requests, and our product control can go into bad hands. It's like one of the top hits. And so no. That is not correct. So the weakness in certificate pinning is this. So imagine you're the organization that owns myserver.com. You're myserver.com. And ultimately you have a TLS certificate for myserver.com in the name of your website. And ultimately the certificate chain will be rooted in some root CA. There may be some intermediate CAs in between. So I've got root CA, CA1, CA2, who knows? And so that's how TLS works. So the problem is that another CA could also mint a certificate for myserver.com. This is untrusted CA in the sense, not in the sense that it's untrusted. It's still in the system trust store. It's untrusted in the sense that you didn't ask them to mint this certificate for myserver.com. And this certificate at the bottom looks like a certificate for myserver.com, and it smells like a certificate for myserver.com, and that's because it is a valid certificate for myserver.com. It's completely valid. And this is a problem, right? Because why? So let's consider that root CA is in the certificate trust store, and untrusted CA is also in your system trust store. So whoever has the private key for the bottom myserver.com can effectively spoof the server or man in the middle traffic, or do whatever they want to do. And if you look at the certificates on your system, like this is from Android Pixel 2 some time back. I think it was about 190. I can't remember off the top of my head. There are lots of potential untrusted CAs in your system trust store. So let's have a look. WooSign, I don't trust them. There's Thought. Okay, I'm good with that. Global. So there's Turk Trust. I don't know if you trust Turk Trust. I'm not. There's also Wells Fargo Bank. There's China Internet Network Information Center. There's no reason to trust any of these, but any of these root CAs could ultimately mint a certificate rooted in one of these CA certificates. And so this is the problem. This is the certificate pinning problem. And how could this happen? Well, there are a few ways. Firstly, you could get the hack CA. Someone hacks the CA, steals their signing keys and abuses their process and starts to mint their own certificates in the name of Did You Know Of, for example. And this is how their hacker got caught, who was trying to intercept Gmail, if I remember, from some dissident in Iran, something like that. And basically, he was using Chrome. Chrome statically pinned to Google's CA, which I think is a global sign or something like that. And so Chrome complained, and he noticed it. So this is the hack CA. You also get the rogue CA. And this is the CA issuing certificates, in this case for Google, and Symantec don't issue certificates for Google. And we have some variations on that. Here's a blog post by the cryptographer Matthew Green. He was ranting and raving about this a lot. And here he's writing about TrustWave. And he says, TrustWave, an important CA and pillar of the internet, took it upon themselves to sell a subordinate cert. In other words, this was their business model. They weren't even hacked or went rogue. This was like the way they made money. And then, the government's got in on the act as well. So this is a French agency. This is a while back, obviously. French agency has been caught signing SSL certs, bit like GCHQ. Oh, what's going on? Don't. Do not. So the idea is, even though the hack CA is in your store of root certificates, it's not in your set of pins. So you just have a restricted set of CAs, root CA, intermediate CA, or end entity cert that you trust, and you validate against that. So if someone else produces a valid certificate chain, you're not going to trust it. About the same time, they were having this debate for browsers, right? You may know about the HTTP public key pinning proposal that some browsers started to support. There was some support, and then eventually they canned this proposal. And the reason they canned it was because they were basically worried about denial of service. Because once a website was pinned to a cert, that was it, right? It would just refuse to connect to that same site with another cert. once it was pinned, whether it was pinned at the server end entity, certificate level, or the root CA or intermediate. And this was a problem if you forgot to update your certs or something got revoked. Basically, you would brick your site until the certificate expired. So they were having this debate in the sort of for browsers at the same time this sort of was going on for mainly like mobile apps, but not just mobile apps. And so 3 months after that post was published, they see something like this. A certain bank realized that their pinned certificate in their app was about to expire, and that would have locked out all their users. And so here they were trying to evoke emergency procedures to give them a new cert. And if they hadn't done this, I can't remember if they bricked their app for a little bit or not, then the app users would have been locked out. So that's just actually a little bit of an aside. That's not the point of this section, but I found it interesting. Another thing about certificate pinning is all the script kiddies, all the bug bounty. It's very easy to figure out if someone wasn't doing cert pinning, because all you had to do was take for example, a burp certificate, stick it in the trust store, system trust store, and see if the app's still connected. If it doesn't, it clearly wasn't pinning because you'd just proxied it via burp. Or you could just break open the app, decompile it, and see whether they were doing anything for certificate pinning. And if they weren't, they weren't. And so people started reporting this, and they got a few CVEs out of it. Eventually, the bug bounty people started saying, please don't submit any more reports about absence of certificate pinning, because it's not actually a vulnerability. What I'm more interested in is how do you actually pin? So what you might do if you're an app developer is you might go to the OWASP cheat sheet, certificate pinning cheat sheet. And if you had gone to the OWASP certificate pinning cheat sheet, this is what you would have seen. You would have copy pasted this into your app, and it's the OWASP certificate. And I'm not trying to pick on OWASP, it just shows getting these things right is hard. And let me break this down a little bit for you. The line at the top says, this is a public key I expect to pin to. So in this case, not pinning to elements in the certificate, but it's pinning to a public key. And then the next few lines down, it says, the one important one at the bottom is, it says, give the built-in trust manager a chance to validate this chain. So is it a valid chain? Basic CA constraints are all the certificates that haven't expired and so on. And is this root CA in the system trust store? And then right at the bottom, it says, it does two things. It says, get the public key from the certificate chain that was given to me, the callback in this trust manager, and compare it with the key I expect. And that's the pinning. However, that had a big bug in it. And the bug is that the server can actually send any certs at once. It doesn't have to be a valid chain. So in this case, the server can actually send two chains. The first chain, you see Z and W. So Z is a valid root CA that has minted a certificate for, in this case, Sigital.com, and that's cert W. That's the certificate chain that actually took part in the TLS handshake. The TLS handshake was done by certificate W. And then what the attacker will do is also go off and fetch the valid chain from the victim and include it in the response to the app. So they send two chains. So the TLS handshake is performed by the first chain, and the pinning, when the actual pinning is done, the compare public key, is done, by one of these certs that you've just relayed, basically. So again, the developer reference, if you go to the developer reference, like what does it say? You're not going to pick this up. It's very vague. You don't know that you're not getting a clean chain in that callback. You're getting all the chains sent by the server. So I've tried to have a more detailed problem definition, pin a certificate to a trusted anchor that actually took part in the TLS handshake. Whether this kind of better problem definition would have picked that up before this even happened, because thousands of people would have gone to the cheat sheet, copied that code, and stuck it in their apps. Whether this would have made a difference, I don't know. But it certainly was it's a very vague problem definition. Do certificate pinning. And this was also this problem was found in a number of libraries as well. So there was a library called OK HTTP, CBE 2016, something about it, and you can read it on the Synopsys blog. One of our guys found it, reported it, and wrote about it in more detail than I'm explaining to you now. But it's basically the same bug. And I wouldn't be surprised if the OK HTTP devs just copied the cheat sheet from OWASP. The point about this is that, if those guys not get it right, that's just an indication of that security engineering, solution engineering is hard and needs to be paid attention to. How am I doing time? I'm already keeping. When did that start? 1:15, right? Okay, that's good. Okay. So the next thing I want to do is talk about tokens and cookies. So here's the problem definition, sort of problem statement. Can we please have all the benefits of cookies, none of the downsides of cookies, but with tokens? And if we can do that, then we get a stateless architecture with at least as secure as cookies. All the benefits, we don't want any of the faff. But if we can have this kind of stateless architecture, then we can just scale as much as we want. It's so easy to scale because we're pushing all the stuff out to the clients. Now, I should caveat this, that this comparison of tokens versus cookies does not actually make sense. Comparing different things here. A cookie is a storage specification as well as a transport specification. It says the cookie is always going to be stored in the cookie jar, and you can also specify how it's transported. For example, secure. It's got a whole lot of rules about whether it can actually be sent back to the website. So it's not. But what can be compared is how people have tried to put this square peg in a round hole. That we can look at. So let's just do a little bit of basic theory and review. So we know how cookies work. They're stored in the cookie jar. The browser attaches them to every request to the originating site. And in the back end, we usually will have some sort of state, like a mapping of session cookie identifiers to actual session objects. And a good thing about cookies is the browser will refuse to send them cross-domain. I mean, if you could get the cookie and exfiltrate it, that would be a different thing. But, cookies are not cross-domain. And that's a good thing, because there's no way you can trick the browser into sending it to an attacker, for example. And this is important because I'll come back to this later. This also means that it's not really possible to write modern apps, because I can't talk to API.other.com, for example. I could do it if they were in the same domain and I had a weekly scope cookie, but it's not the way things work in Web 3. Tokens, on the other hand, the idea here is that we take all the states and we just shift it over to the client, and we sprinkle a bit of integrity. Maybe you want a bit of encryption because you're worried about confidentiality of some fields. And the problem with this diagram is not just what's in it, it's what's not in it. A lot of these things are implicit, like the access control is all under one domain. There's an access check for every request. The user identity. If you wanted to escalate privilege for the user, like as in a role, you could challenge them to re-authenticate, and you can have a flag associated with the session. And it sounds obvious, but the session object is not shared with other parties. I mean, that's like just an obvious thing. It's here. In traditional websites, it's here in the server. Sounds like an obvious thing to say, but actually when we move to cookies, some of these things start to break down. Tokens. So if we look at tokens, and let's imagine I have a single page application, I have tokens here. With a token, typically is set in the authorization header as a bearer token, which means what's in the token grants the requester access to the requested resource provided the access token allows it. And here the typical way of doing is sticking in the authorization header. And of course, there's no reason why you couldn't talk tokens now to the main site. So you could start to split out the site into the static elements and the API elements. And there's no reason you couldn't put a token in a cookie, right? You could do that. It's just a string. And that's a problem. This becomes a problem because unlike the cookies, now, because the developer is responsible for attaching, because you have to write JavaScript code, you'll use a library, but JavaScript code to attach the cookie in the authorization header before you send the request. And that means you can make mistakes. So like really simple, easy mistake to make is like, imagine you're doing an allow list. So you don't want the situation of sending it off to the attacker. So you write something like, if your URL starts with https://mysite.com, then that's okay. So like an obvious attack is just that's just a very feeble attack. mysite.com @attacker.com, and this will bypass such a trivial check like this. But then you get to like more complicated URLs, and the browser, by the way, does this already for you, this kind of stuff. But now you have to reinvent the wheel, and URL parsing is incredibly tricky, and there are always bypasses published. But you have to write this yourself, or no, you use a library for it. But still, this is not a good thing. So there are only two slides on theory in here, I promise, because I just need to talk about this before the next few slides. So the first is just to give you a quick theoretical 5-second review of OAuth 2. In OAuth, you have the concept of a resource owner who's trying to delegate access to an entity who will act on his behalf to access some resource managed by the resource server. And in order to do so, via the user agent, the resource owner will get an access token to the OAuth 2 client who wants to access the resource. So an example would be, I've got a whole lot of photos stored somewhere in some cloud storage provider. I want to make use of a cloud printing app to print those photos for me. So what do? I permission the photo printing app. I permission the photo printing app to print a selected, a restricted set of resources. And the OAuth 2 is just about doing a dance to get this access token to the OAuth client that's going to act on my behalf. So the OAuth client is going to get the access token, and then it's going to present the access token to the resource server. And the resource server is going to look at this token. It's going to say, what is this thing? And in the modern web world, these two entities, even though they're logically different, they're put together in the browser in a single page application. So a single page application, the client application and the user agent are one and the same. Last little bit of theory for you. We need to distinguish between an opaque token, which is just a reference to another token, and an assertion-bearing token, which encapsulates its own set of claims. So the claims are part of the token. An example of that would be a JOT. So JOT is a header which says how this thing is protected, a set of claims is a payload, and an HMAC or signature, which is the integrity protection. Whereas an opaque token is just a string that the authorization server can use to look up a key value pair. And that means it needs to maintain state. And the other thing that needs to happen with opaque tokens is because the claims are not part of the token, it requires an extra round trip. The resource server gets the token and a request from the OAuth client and says, what is this token? So it needs to go off to the authorization server by something called an introspection endpoint, and the authorization server returns a set of claims. And then the resource server can say, this is Bob. He's trying to print the photos, and I've got an access token that allows whoever this is to do so. And this leads to our sort of next kind of vulnerability, which I'm calling a confusion BOGOFF. It's a confusion, buy one, get one free. So in a confusion BOGOFF, we have a confused deputy problem, and we also have a token confusion attack. So imagine that I have an evil OAuth client, and it's got an access token for Bob, a valid access token for Bob. And I have a confused OAuth client. An evil OAuth client is going to try to spoof Bob. And what's important about this scenario is that evil OAuth client and confused OAuth client both share the same, both trust the same, they use the same authorization server. So while Bob is using evil OAuth client, eventually, as part of OAuth, he'll get a token. And an evil OAuth client can then use that token and present it to confused OAuth client. And confused OAuth client is going to say, what is this? I have no idea what this is. You've just given this bearer token to me. And it's going to say, okay, authorization server, what is this token? You're trying to do blah, and I've just received this token. And the authorization, the introspection endpoint is going to return a set of claims. And one of them is going to say, users Bob. And the confused OAuth client is going to say, you must be Bob. How do we know that you are Bob? Well, it says right there. It's in yellow, Bob. And so in this way, evil OAuth client can spoof Bob to the confused client. And this is a BOGOFF confusion attack, because this is an access token. And it's being abused as an identity token. This was a vulnerability that happened quite a few sites. Now, this was kind of solved with OpenID Connect. And they introduced a standard set of claims, and one of them was the audience. Who is the audience of this token? So in this case, OpenID Connect solves this because the audience for this token is evil site. So when confused site gets the token and says, who is this for? It's not for me. I'm going to reject this token. And in this way, the evil OAuth client can actually, just as you do with session hijacking, you present a token that says Bob to confused client, and then confused client says, you must be Bob. I'm going to log you in. And now you can do all the things that Bob would be able to do. So the need for identity and session management didn't go away. There was still a need in these apps for this kind of stuff. It just got lost in the sort of transition from cookies to tokens. But these kind of things were implicit in the original solution. And there are, I'll give you, I'm not going to go through the bottom one, but there are more examples of this kind of thing. So an example would be malicious resource owner wants to access the admin interface on the site. And they have a token for Bob that says role admin, but the scope, which is the permission, says view. And so in this case, the server should reject it. Or another example would be at the bottom, Bob has two tokens. He has an identity token that says who he is, and he has an access token that's also has the permission view, whatever the view permission might mean, and that's in the part of the scope claim. Now we see this kind of thing, this sort of thing happening a fair bit. So there are sort of new opportunities for authorization failures. Something similar to this actually did happen with Facebook, the view as feature. Not quite the same thing, but you could view something. What would it look like if I was someone else? I don't use Facebook, but most of you probably use Facebook. But the problem there was what Facebook did was it dished out a token that actually wasn't just restricted to viewing the resource, right? You could do a whole lot of other stuff. So it's just an over-permissioned token. So somewhat similar, not quite the same thing. So another question is, where can I store the token? I have this token. I'm in the browser. What do I do with it? You've got a few options. You can try and hide it in the DOM. Maybe you stick in the DOM somewhere. Maybe you split it up into multiple components and you cleverly reassemble it. You could use local storage, session storage. You could put it in the cookie jar. It wouldn't be HTTP only. It might be secure, but it wouldn't be HTTP only anymore. You could do that, and there's probably some more advanced things. So the problem is, a cross-site scripting attack can modify or read this token because that's by definition. You stick in the DOM, you stick in local storage, whatever. You have an XSS, it can read that token and exfiltrate the token. I should point out that if you have an XSS, that's probably stealing the token is probably the least of your worries. But so this is called dubbed sidejacking. It's been dubbed sidejacking quite a long time ago. I don't like the term, but I never, when I saw sidejacking, I had no idea it doesn't tell you what it means. But sidejacking is effectively reading the cookie or the token and exfiltrating it. So I shouldn't be able to steal a session cookie this way because it would be HTTP only. But I could steal a token this way. So what do you do about this? Because now this is less secure, somewhat less, very small, like exploit vector, but still. You could do a few things, there's some clever tricks. I won't go into them, but they don't actually solve the problem. They just make it a bit harder. What does OWASP say? I'm not knocking OWASP, by the way, just a caveat. But what do they say? So they say about sidejacking, use a cookie. What you do is you generate a cookie with a special random value, and you hash that random value and stick it in the token. And so this doesn't actually prevent sidejacking. It just prevents you using it from outside of the browser session. Because if I steal the token, try and play it from somewhere else, I'm not going to have this cookie. But I found it kind of ironic that this is not a this does not prevent it. It just binds it to the user session in the browser. But I find it somewhat ironic that they're recommending using a cookie to protect a token. And once you do this, you lose all the other benefits of tokens. It's really then it is bound. It's not cross domain as a token would be. So this has a happy ending, maybe. This is kind of new. So what there's a bit of consensus now is that you should take those tokens back out of the browser and move them back to the server, move them back to the back end, which is they've been moved to the client side, and now they actually put back in the back end. And what you do is you sort of move the logic of the OAuth logic, you rip it back out of the browser, stick it in the back end, and then you can securely manage secrets. And then you replace the communication between the browser and the server, and this is the back end for front end pattern, which is very similar to the API gateway pattern. But the idea is it services a single type of client and does, it's the single responsibility principle, do one thing. And so what happens is that you use a normal session cookie for session management, put the tokens securely in the backend, and then this backend can be a confidential OAuth client, so it can actually authenticate to the resource server. So, summary. Fixing things is actually quite hard. Defining the problem correctly is really, 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 really important. So a lot of problem domains have implicit properties that, because they're implicit, like the cookie, all of these things were not sharing trust with another site. This was all sort of implicit properties of original architecture that is, because they were implicit, you sort of forgot about it. So it's easy to miss them. You will be hit by curveballs from time to time, even though you spend a lot of time breaking stuff. You'll need to write a mitigation, and sometimes actually thinking about that, how you fix that, is not quite as easy as you thought it would be. But just awareness of that fact is a good place to start. Thank you.